Hi everyone, this is the first topic presentation for your first chapter, States of Matter, and mainly we're going to talk about on the properties of gases like temperature, pressure, volume, and especially mole concepts. Okay, now let's start with the gases. Now there are four important properties of gases. Probably you're going to just remember from your lectures, the lectures from last year. It is pressure, it's volume, mole, and temperature. So let's see what is pressure. In fact, the general formula for pressure, it is the force acting on a unit area. Now, what is the unit of force? This is Newton. Area is meter square. So if you have as Newton, if you have that one as meter square, when you divide them side by side, this is going to be Newton per meter square for the unit of pressure, which is also known as Pascal. But for gas pressure in daily life, we do not use Pascal. We use some other units like atm or bar or millimeter mercury or centimeter mercury, and another one is we have torr. So this is the unit conversion table for pressure. You see bar here, Pascal here, bar, atm, torr, millimeter mercury. So for example, when you have atm here, you can see when you just get the connection here, you can see 1 atm is equal to 101,325 Pascal. So these can be really mixed up. So let me summarize it for you. Okay, 1 atm is equal to 760 millimeter mercury. Or you can also say that 760 torr. So the knowledge that you're going to derive from this numbers, 1 millimeter mercury is equal to 1 torr. Okay, let's continue. You have 76 centimeter mercury. You have 1 atm also as 1.013 bar. 1 atm is equal to 101,325 Pascal, and final bar is 10 to the power of 5 Pascal, which you can also say has 100,000 Pascal. So let's start to learn how to measure pressure. Now, there are two types of pressure that you can measure in our lecture. The first one is the atmospheric pressure, and the second one is the pressure in a closed container, pressure of a gas in a closed container. Now, this is the important word here is now barometer. This is important. Barometer is used to measure atmospheric pressure. So following pictures is represent Torricelli's experiment. Now remember, Torricelli has done this experiment at sea level, and it was 0 centigrade degrees. Because going upwards, going to top of a mountain or changing the temperature probably will change the height of the mercury that he had measured. So you have a full of mercury here, and he just measured that height as 76 centimeter. Now that part of the tube is empty. Let's say that this is vacuumed. So this direct height will give you the exact value of atmospheric pressure. So let's discuss on why he used mercury. First, of course, this is a liquid, but you can say that water is a liquid, but water's density is 1 gram per centimeter cube, where mercury's density is 13.6 gram per centimeter cube. So using density with this, using mercury with this high density, will allow you to use a shorter tube. So now we have the manometers. Now manometers are used to measure the gas pressure in a closed container. So here are the types of the manometers. Now you are seeing 6 manometers here. Now 3 of them are going to be open-end manometers, where the other 3 are going to be closed-end manometers. So let me close these ones. Okay, now I'm drawing. You have X gas here. Let's say that also X gas here, also X gas here. So let's say you have a mercury level difference as H here, and you have some coming P0 here, or let's say that this is going to be no mercury difference. Again, there is PO. PO means atmospheric pressure. Let's say that the mercury difference will be on the left hand side, not the right hand side, but again you have P0 here. So these are, let me just divide it like this, open-end manometers. These are open ends, and these are going to be closed-end manometers. So for the other ones, let's say that you have Y gas here, again Y gas, again Y gas. So let's say that initially there is a mercury level difference here with a value of H, but this case this is empty. Let's say that for this one you have again mercury level difference of H here. Let's say that you have another gas here. Let this be the Z gas. Then we draw this vice versa. There is increase on the left arm of the manometer. Again, there is some H here. Let's tell that in this case you have some T gas here. Okay, let's compare these ones. The first one. Now you have the X gas here, and you have the P0 here, and you just have a mercury level difference. Now if the mercury just increases on the right hand side of the manometer, this means that this is X gas has a higher pressure than P0, and the difference is, in fact, there is H here. So you can write equality like this. Px is equal to P0 plus H. Now what about this one? You have again X here, you have P0 here, but in this case you do not have any mercury level difference. So what is going to be the case? P0 is equal to Px. Now comes the third one. Now the third one, you see that in this case there is a mercury level difference on the left hand side of the manometer. So this means that P0 has a higher pressure than Px. So how can you write the equality? P0 will be Px will be equal to P0 minus H. Now these are the open-end manometers. Now what about the closed ends? For example, this one. This is Y gas here. There is an empty place here. There is no gas, no air, nothing else. And there is only a H difference here. In this case, this H cannot be told as the difference, but directly the pressure of the Y gas. So you can write it as Py is equal to H. Now this one, Py is equal to Pz plus H. Why? Because H difference on the right hand side, this means that Y exerts really high pressure than Z. So its pressure is going to be higher than Z. Now this comes the third one. The third one is vice versa of this previous one. In this case, pressure of Y is going to be lower than pressure of T. So how you can write it? You can write it as Py is equal to pressure of T minus H. Now comes the volume. Volume is the amount of space that specific amount of matter occupies. So if you're talking about the gases, the volume of the gases is ignored and their volume is directly equal to volume of the container. Now what are the units of the volume? 1 decimeter cube is equal to 1 liter, or this is 1000 milliliter, or this is 1000 centimeter cube. So let's write let's say that there is another unit here, millimeter cube. So millimeter cube will equal to 10 to the power of 6. So I go to this one, then let's say that 1 decimeter cube is equal to 1 milliliter, 1 decimeter cube is equal to 1000 centimeter cube. This is equal to 10 to the power of 6 millimeter cube. So the knowledge that you should derive from this data is 1 decimeter cube is equal to 1 liter and 1 centimeter cube is equal to 1 milliliter. Okay, now the temperature. In fact, temperature is an indicator for average kinetic energy of a substance. Now, average kinetic energy of a substance can be calculated by using a formula 3/2 times R times T. Now, we're not going to use this formula in our mathematical problems, but just I wrote it to let you know that the kinetic energy is directly equal to proportional to that T. So this means that when the temperature is increased, average kinetic energy of a substance increases also. So do the volume, of course, if the gas is found in a container with a piston, and speed of it. And this explains the working principle of thermometer. As you know that in thermometers we use mercury, but nowadays, because that the mercury is poisonous is known, other than mercury we use some special alcohols. Now comes the units of the temperature. We have Celsius, we have Fahrenheit, and we have Kelvin. Now Kelvin is very important. In most of the mathematical problems in physics and chemistry, we use the unit of Kelvin. It is known as absolute temperature. The difference from Celsius and Fahrenheit, there is no negative sign of Kelvin. For example, you cannot say minus 40 Kelvin. This cannot be the case. So let's look at those unit conversions of pressure. Kelvin is equal to Celsius plus 273, or Celsius over 100 is equal to Fahrenheit minus 32 over 180. And finally, the lovely one, this is the mole concept. Now, as you know, we started the mole concept in the classroom. We solved lots of questions. I'm going to solve some of the questions also here one more time. And if you still have any question, please do not hesitate to ask. Okay, first we start with saying the relative atomic mass here. Now, some of the atoms, for example, oxygen's mass number is 16. We have nitrogen as 14, or we have, what else? Helium as 4. In fact, in nature, the mass number of oxygen is not that a good simple number. It is something like 15, 9, 9, 8, 2, and goes like this. And nitrogen 14.0025, it goes like this. So in order to have better calculations, the scientists decided to accept the carbon's mass number as 12.0000. So they just arrange all the elements' mass numbers dependent on this carbon atom, and these mass numbers are called relative atomic mass. And any substance, this one, any substance that contains Avogadro number of particles is 1 mole. Okay, for example, one water molecule contains 3 atoms. Why? I have 2 hydrogen here and 1 oxygen here. 1 mole of water molecules contains. Now saying 1 mole, saying dozens, saying bunch doesn't differ from each other. 1 dozen means you have 12 that particle, or 1 bunch says you have 10 of that particle. If I say 1 mole, I have Avogadro number of particles, which has a numerical value of 6.02 times 10 to the power of 23. Or 1 mole of water molecule contains, in this case, 3 moles of atoms, because again, related to this one, if 1 molecule contains 3 atoms, then 1 mole contains 3 moles of atoms. Okay. 1 mole of water contains how many atoms? The question is how many? Now, as in the previous slide, we said that there are 3 moles of atoms here. So these 3 moles of atoms refers to the Avogadro number of atoms. Now comes the mass. Now, in the beginning of the question, you see that there is oxygen is given as 16 mass number, where the hydrogen is 1 here. Now let me write the direct ratio. 1 mole of water contains 1 mole of oxygen, which weighs 16 grams. So the answer will be 16 here. Or 0.2 mole of water molecule weighs how many grams? So this is my question. Okay, let me write the ratio. 1 mole of water, in fact, weighs 18 grams. Why? Because I have 2 hydrogen here and 1 oxygen. This will give you 2 grams and this will give you 16 grams. When you sum them up, it's going to be 18. So if I have 0.2 mole of it, what's going to be answer? 3.6. Okay. Final one. 5 mole of water molecule contains how many grams of hydrogen? In this case, a specific atom is asked. So here is my ratio. 1 mole of water contains 2 grams of hydrogen. So if you have 5 mole here, this means that you're going to multiply by 5 and lead up to 10 grams of hydrogen. Okay, this one. Now, STP and RC, they are some kind of conditions. Now, what are they? STP is standard temperature and pressure, which is 0 centigrade degrees and 1 atm. So, what is the important about it? At this condition, 1 mole of any gas occupies 22.4 liter of volume. Now this is the first one. Now comes the second one, which is RC. Now RC stand up for room conditions, which is 25 centigrade degrees and 1 atm. So at this condition, 1 mole of any gas occupies 24.5 liter volume. So as we said, there is 1 mole here and 1 mole here, and in the question it is asked 2 moles of sulfur dioxide. So this means that you're going to multiply all these numbers by 2 and get the answer. This is going to be 44.8 liters. When you multiply by 2, it is going to be 49 liters. Okay, this one. The oxygen that has this amount of oxygen atoms is how many moles? So if you have just like a number like this one, please turn it into mole, like 6.02 times 10 to the power of 23 oxygen atoms is 1 mole. So what about 1.204 times 10 to the power of 23 oxygen atoms? How many? So this is going to be 0.2 mole of oxygen atom. So my question is asking the mole number of that oxygen. Now when I say oxygen or oxygen molecule, you're going to understand the O2 molecule. This is really important. So the final ratio will be 1 mole of oxygen contains 2 moles of oxygen atom. So what about 0.2 mole of oxygen atom is found in how many moles of oxygen molecule? And the answer will give you 0.1. Next one. 6.4 grams of oxygen atoms have how many atoms? Now as you know, oxygen is 16 as the mass number. So oxygen atoms it says, so 16 grams of oxygen is 1 mole. So what about 6.4 grams of oxygen? How many? It is going to be 0.4 mole of oxygen. So if I ask you to find the number of atoms, this means that you're going to multiply this number by the Avogadro. So 0.4 times the Avogadro number equal to 2.408 times 10 to the power of 23. So this is the big long number that you're going to write here. And then final 2 questions. In this case, I have given you 6.4 grams of oxygen molecules. Let's write first its small number. If I say oxygen molecule, you're going to understand O2 molecule. So 1 mole of O2 is 32 grams. So what about 6.4 grams of it? It's going to be 0.2 mole. So 1 mole of oxygen is 2 moles of oxygen atoms. So what about 0.2 mole of oxygen? How many moles of oxygen atoms? It is going to be 0.4 moles of atoms. So if the number of atoms is asked, this means that you again will multiply that number with Avogadro, and again you're going to have the same answer as the previous one, which will give you 2.408 times 10 to the power of 23. So same molecule or atom does not differ if you have the same mass of that substance. And finally, find the mass of the oxygen. This is my question mark. If it has this amount of oxygen molecule. Now, as you know, 1 mole of oxygen contains Avogadro number of particle, and 1 mole of oxygen in fact is also 32 grams. So if I have this amount of molecule, how many grams of oxygen do I have? This is going to be 3.2 grams. The answer will be 3.2 grams. I hope this video will help you to understand those problems. If not, please come and ask me.